Hey, nice if you're here again. Hopefully you watched the first version of the video with regard to the dome and the waters above. I would like to do something now as well, and that is trying to calculate if there is water, if there are waters above or there is water above, what would be the volume and the weight of that water pushing down on the dome. So let's have a look. We'll go outside where I do the rest of my introduction, and then we'll come back for some calculations. Thank you. Oh, already like, subscribe, put the bell on, then you get also the updates for the other dome related videos I make. Let's go outside. Hi, here I am again. In the previous video we showed that somehow the water doesn't want to stick on the dome. And that should be the case, because that is what you flat earth believe. Let's assume for a moment that water wants to stick here. There's no law created by your God that would give a reason for it to stick. But let's assume. If we look at the pictures, we always see a dome and then an amount of water. And the question is, how much should that be if it sticks? Because again, previous video it didn't stick. Would it be something like this thickness and then round? Well, we have figured out that this height must be about 20,000 kilometers. And this thickness would be a layer of water of a couple of thousand kilometers. Hey Shirley, it's one of the cats. He is coming to have a look. Yes. So I don't think that's really a good way to go. Maybe a little bit less, like this. But still, that would represent a lot of water. I think that if we would go for maybe 1%, that the layer of water, if it sticks, is like this thickness. Could we agree on that? And how thick is that? Well, I'll show you another interruption of the video where I measure this as 12.1 centimeters. And so the first thing I thought, let's try to see how big is this thing. It's about 12 centimeters. This is about 1.2 millimeters. So if we now compare and we assume, and I will explain that later, that the height is 10,000 kilometers, then that would be 100 kilometers. 100 kilometers of water. And what I now want to do is calculate how much water is that, and what is the weight of that water. So how do we calculate that? We will start with taking this down a little bit, because all I need is 5,000 kilometers on the Tropic of Capricorn. And from there we can see that a oblate spheroid, nice word, oblate spheroid, and then half of it, of course, as a dome would fit the flat earth model. But it would have to be like that, and it means the height would be like 10,000 kilometers. That's where your polar star would be on your flat earth dome. Then the moon and the sun still can turn their rounds inside that dome. And how do we calculate the amount of water? Now we take our oblate spheroid and we will calculate the volume of that, and then we will take the same oblate spheroid with a larger radius here of an extra 100 kilometers, and we will subtract them, and what we have left is this small, very thin layer of water and we will have the volume and the weight of that. So that is how we're going to do it. See you in the studio or the man cave, whatever you want to call it. Some of the flat earthers call their kitchen or their garage a studio. In my case, it's just my working room or man cave. See you there. So we're back. Let's do a resume of the points we addressed last time. The flat Earth claims are as follows. The Earth is flat. Water seeks its level and therefore water doesn't bend. Gravity does not exist, so water does not cling to a ball. Water needs a container, like the ice wall on the largest scale of the flat Earth, and God created the dome with waters above. Some part we discussed in the previous video, and now as we said, we're going to see what then the volume and the mass of that amount of water on top of that dome is by approximation. We agreed to keep it very small, like 1% of the dome would be water, because otherwise it would be a huge amount. And we still need some water, because otherwise when the gates open you can't have a total flood. Look at the picture. We need some figures to calculate the volume of a spheroid, and as we said, we need two values, one of the dome itself and then one with the water included, and by deducting the one from the other, what we have left will be this little thin dark blue layer of water and the volume of it. Now, we know that Gleason said that the sun must be at least 5,000 kilometers high, which I think if you would do some kinds of measurements, it could be a justifiable solution, as long as you think that the Earth is flat and the sun goes above it. Recently, a flat earther here in the Netherlands showed me a test he did himself, but the result there was that the sun would have to be 7,000 kilometers high. Now, the distance from the North Pole to the Tropic of Capricorn is then 12,500 kilometers, and the radius from North Pole to the ice wall would be 20,000 kilometers. And if we would do as if it is a total dome, then also the height would be the same as the radius here, 20,000 kilometers. And he said that is probably too big and way too high, and you would need even more water. So we said, well, as long as Gleason's sun can, without bumping into the dome, can make its turns, and the moon as well, then this would be a good approximation of what the dome could look like. It would be a oblate spheroid with a height of 10,000 kilometers and a radius of 20,000 kilometers. That's what we see here in the left top. And then we ask AI to calculate the volume for us. And that's here you see the core of that calculation. And then we get a value in cubic kilometers. Now, the next is the spheroid including the water. And we said that's then when it's 1% of the height of the 10,000 kilometers, then it's still 100 kilometers thick, the layer of water. So we can calculate the volume of spheroid B. And then what we need to do is deduct the two. And we get the difference in volume, which would then be only the blue part here. And the difference in volume is then 3.0 4 times 10 to the 11th cubic kilometers. Now, we still need to do one thing, because we were calculating with a oblique spheroid, and that means we also calculate the bottom side. Yeah? It's then like a ball, a rugby ball. So in the end, we will have to divide by 2. And that's what we do. Now, then I asked, what if that difference in cubic kilometers would be water? Then we calculate what the total mass of that water is. And you will see here that would be 3.3 times 10 to the 23rd kilograms. So we have to divide the volume by 2, and then the mass of that volume is 1.7 times 10 to the 23rd. That is a humongous big amount of water and a humongous weight. That's a 1.7 with 23 zeros behind it as weight in kilograms. Think about that. Would that be possible? Compare it with the oceans of our globe. The approximate Earth's ocean volume is 1.33 times 10 to the 9th. So we talk about a difference of a factor of 125. So with the used radii, we can see that you would have 125 times the volume of all Earth's oceans together, just to have waters above on a dome. Now we find it, flat Earth believers find it very difficult to believe that a small part of these 125 being the original value of the waters on a globe, that can stick to a globe and doesn't fall off. But they have no problems, and you, if you are a flat Earth believer, apparently have no problem that 125 times that amount of water can simply stay on a dome. Think about that. I'm not going to say you're right, you're wrong. I'm just giving you this thing to think about. Like the first video and the third video, we will do, we will have a look at what happens with all that weight. Is that even possible? And how do we know whether it is or is not possible? But I'll see you then. If you subscribe and you click on the bell, you will get a pop-up the moment I have the other video ready. So please like. If you don't like, please comment. Tell me what you think is wrong about my reasoning. I'd like to hear from you. And for now, bye-bye.
Don't know much about history, don't know much biology, don't know much about a science book, don't know much about the French I took.